We did the topology unit when we did, because I need some facts that come from the topology unit in these bits. But I'm going to change focus back to sequences. Any one of these?
Sure. Okay.
Low attendance today. I mean, like, I should. I print out enough I've already done. Yes. So, the next two things on the to-do list for stuff I want to build are two remaining facts about convergence of sequences. And they're similar in spirit to the monotone convergence theorem. So you know what? Remind me of the monotone convergence theorem. I don't need like the exact wording, but like what does it do?
Something about it is increasing or decreasing, strictly increasing or strictly decreasing. And something about convergence setting.
Yeah. So the conclusion is that it converges. And let's use the more vague one where like, what's the word for increasing or decreasing? It's in the name of the theorem. Monotone. So instead of saying increasing or decreasing is if AN is monotone and bounded, then it converges. Here's the question though, like, we proved one implication. It's an if then, we proved that if then. Is the converse true? Is every convergent sequence monotone and bounded? What counterexample you may be thinking of?
Oh, like -1 to the n or something?
Yeah, something with -1 to the n. That doesn't converge, so it's not good enough yet. But let's muck around with that. -1 to the n, it doesn't converge, so I want something that does converge but fails that. What could I do to -1 to the n to make it converge? I like that it wiggles up and down, but it wiggles up and down too much. Let's make the wiggles
something
get
that
small.
has a wiggle and then flats out to a value.
Yeah, something that's going to wiggle and flatten out. Will that do? Yeah, cool. Not monotone, does converge. So the converse is false. So if I ask you to show a sequence converges, you can try to use monotone convergence. But it might be that the sequence in question isn't monotone, in which case you can't use monotone convergence. It doesn't tell you anything. A tool that does, and is an if and only if result, is the Cauchy criterion. So a theorem, a sequence is convergent if and only if it is Cauchy. Oh, off the screen. So there's a condition called the Cauchy criterion. If a sequence satisfies this Cauchy criterion, then it converges, and the opposite. So if you have a sequence that fails to be Cauchy, you also know that it doesn't have one. And I guess maybe I should state the Cauchy criterion. Definition 6.1.1. A sequence is called Cauchy if for every epsilon there is a big N, such that if M is bigger than big N and N is bigger than big N, then AN minus AM is less than epsilon. So, excuse me. I'm going to put the definition of Cauchy and limit on the board, and we'll do a quick compare and contrast. And maybe this is a good chance. What's the definition of AN converges to L? Nice. So informally, no matter how small an epsilon, well, no matter how close you need AN to be to L, as long as you look far enough along the sequence, AN is that close to L. The Cauchy criterion says for all epsilon bigger than 0, there exists a big N such that if M and N are bigger than big N, then AN minus AM is less than epsilon. So a sequence is Cauchy if, no matter how close you want the terms of the sequence to be to each other, as long as you look far enough along in the sequence, they are that close to each other. So a sequence converges to a number if the terms of the sequence all cluster around that number. A sequence is Cauchy if they just cluster around each other. The Cauchy criterion says that if a sequence is Cauchy, then it converges inversely. Now, before we get fancy and prove this theorem, let's use it. So maybe I'll put the big theorem that we will prove today. Maybe a little informally written. Let's use this to prove that a sequence converges. Here's the sequence I'm going to study. Let's let big Sn be the sum from k equals 0 to n of negative 1 to the k all over 2 to the k plus 1 as described by that sum. I claim that that sequence converges. Now, a thing you might do, right? If I ask you, if you're in Calc 1 and I ask you, what's the limit of the sequence? You're going to say, well, let's just plug in n equal to 1,000 and then 10,000 and see if it seems to stabilize close to 5. Then I'll just say the limit's 5, call it good. If you plug in 1,000, you get something that's about 0.29430. That's not so helpful if you want to say what the limit is equal to. It's somewhere around 0.29430. So we won't be able to use the definition of the limit to prove it converges somewhere. We don't have an exact candidate for the limit. We need to do something else. Thus, the Cauchy criterion. So let's try to prove that this sequence is Cauchy. And all right, so there's a paper that I'm reading right now that's a math paper. And it definitely doesn't do the thing where it starts a proof with a good, strong want-to-show statement. So you wind up having to flip back and forth through it. Here's a nice, strong want-to-show statement. We want to show that sequence converges. In light of the fact that convergent if and only if Cauchy, it suffices to show that this thing is Cauchy. So let's prove that that is Cauchy. So I need to prove a statement like this. So you want to prove something is true for every epsilon bigger than 0. So the first line of your proof better be consider any epsilon. You need to show there exists a big N such that some stuff happens. I'm going to try to come up with a big N, and I'll hopefully have this thing designed correctly so that I can just fill in the blank once I know what big N has to be. I'll then consider any M and N bigger than big N, and hope that that difference is less than epsilon. So, shall we try? And what do you think? This proof isn't going to seem that unfamiliar. It's going to look like a limit proof. It's just a different thing I want to show is small. So let's do it. So let's consider any epsilon bigger than 0. Let's let big N be something that I'll put in that blank once I know what I want to put there. I don't think I had any intuition. Let's consider any M and N bigger than big N. Would that difference be the same if I swap the order? So I may as well assume that the bigger little n is before the little n. So rho log, I will assume that little n is bigger than or equal to little m. They might be equal. Then I guess the difference would just be 0, which is less than epsilon. So by expanding out the definition of both Sn and Sm, we get Sn minus Sm in absolute value is equal to that. Nothing is happening. All right. So we've done a few things like this with canceling common terms of some series, I think. Those two series, do they have some terms in common? Yeah, they have the first term in common, or the zeroth term in common. They have the first term in common. They have all the way up to the mth term in common. So let's cancel out the terms they have in common, and maybe even terms with k less than or equal to m. All of this will go away. I can now replace this sum with the sum that starts at m plus 1. That feel pretty okay? And that's an improvement. I'm going to, for emphasis, put the absolute value of errors in blue so that they don't disappear. So here's the next thing that I'll want to do. That's an absolute value of a sum. Can you just move some absolute values inside of a sum? Certainly not with equality, right? Like, but we do have a triangle inequality, right? The triangle inequality says that if you do put the absolute values inside of the sum gets bigger. And in fact, this is a great example of it. Instead of the negatives and positives trying to cancel, they'll all team up and work together. So, let's use the many-term triangle inequality to rewrite this as less than or equal to the sum of the absolute value of negative 1 to the k divided by 2 to the k plus 1. Well, it's from k equals m plus 1 up to n. And I'm just like messing around right now. What else could I do to simplify that? So the negative 1 to the end just like introduces a minus sign half of the time. Does that matter? That absolute value fills it. The denominator, is it positive or negative?
Positive.
Positive. So do the absolute value of errors matter after I erase the negative 1 to the end? Cool. So what's this equal to?
1 over 2k plus 1, 2k plus 1.
Nice. And I've used that. The absolute value of negative 1 to the end is 1. That looks like it's getting close to a sum that you like understand really well, right? That looks like a geometric sum almost. It's just off by that plus 1. And remember, when you're trying to prove that something is small, if you keep on like making it bigger without accidentally making it not be small anymore, then you're fine. If I erase that plus 1, does it just get a little bit bigger? Yeah, let's do that. Because 2 to the k plus 1 is bigger than or equal to 2 to the k, which is positive. In fact, this is a strict inequality. Let's use that as strict. So this is strictly less than the sum from k equals m plus 1 up to n of 1 over 2 to the k. And I don't know, that's like a geometric sum, right? It's a geometric sum that like starts at m plus 1 instead of starting at 0. I don't know the formula for a geometric sum that starts there. You could probably look it up. Like it wouldn't be that bad. Instead, I'm going to turn this into a geometric sum that does start at 0. I was like, what is this? This is like 1 over 2 to the m plus 1 plus 1 over 2 to the m plus 2 plus 1 over 2 to the m plus 3, da 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 da.
So subbing out k for m plus k, so k is m.
Yeah, let's reindex this so the power starts at 0. So that means I guess I should factor out all the stuff that I can. So how much am I going to factor out?
M plus 1.
Yeah. Let's factor out that 1 over 2 to the power m plus 1. So this thing is now strictly less than 1 over 2 to the m plus 1. And that m plus 1 should make you happy. 1 over 2 to the m plus 1 gets small as little m gets big. So as long as like the rest of what I write doesn't get big, we win. So, times the sum Let's see, that'll be power of 0. So all of these are going to get reduced by m plus 1. So the biggest power will now be n minus m minus 1. So it'll be the sum of still 1 over 2 to the k's. K equal to 0 up to n minus m minus 1. All right. That's now a geometric sum that I know a formula for. Oh, you know what? Yeah, I'm going to follow the actual language that's written here. Oh, no. Should I use the formula for a geometric sum or a formula for a geometric series?
It's been too long since that, I really
So,
Okay. Do you know the formula for a geometric sum?
1 minus r?
Ooh, that's for the series.
Oh, okay.
But that's fine. If you only use finitely many terms, it's smaller than than if you used all of them. So this is less than, I'll leave the 1 over 2 to the m plus 1 behind, times 1 over 1 minus r, which is 1/2. By using the formula for a geometric series. Cool. All right. We doing all right? Let's try to simplify that. What is that silly looking fraction equal to?
2.
2. So I just need to multiply this by 2. Is that easy? Did I do it right?
Pretty sure.
All right. So let's go back to what we wanted. So all of that corresponded to using the geometric sum instead of a series. So I want 1 over 2 to the m then to be less than epsilon. And I get to make little n be bigger than big N. So that's certainly less than 1 over 2 to the big N. Can you set that equal to epsilon and solve for big N? Yeah. What'd you get? You are allowed to use logarithmic functions even if we haven't justified them. So what's big N?
My purpose that was
Well, this is scratch work. We can write more steps. You want to solve that for big N. What should you do?
I would first pick.
Should it go through the log?
Put them both in the log. Let's use log base 2. Cool. We feeling good? We now have our trace of big N. Let's let big N be the log base 2 of 1 over epsilon. So I can use that little m is bigger than big N is equal to log base 2 of 1 over epsilon. So far we have Sn minus Sm is less than 1 over 2 to the m. And now this should feel like super familiar, like it's the end of a limit proof. That's less than 1 over 2 to the big N, which is equal to epsilon by our choice of big N. Neato. That feel pretty okay? So, this sequence is Cauchy, and so it converges. I don't know where it converges, but it converges.
Do you think it's common that we'd have to use this many inequalities for a Cauchy proof, or is this kind of?
I mean, I think this one was complicated just because like the input was complicated. Maybe for the sake of pulling back the curtain and showing you what I expect on homework. The thing I'm going to have you do on homework is something that's going to look pretty similar.
Okay.
So chances are it might be a similar amount of work. You might be able to like streamline some things. Cool. All right. So, on to the actual proof. So the proof is convergent if and only if Cauchy. The easy direction will be convergent implies Cauchy. And that should, I think, seem pretty intuitive. Cauchiness requires that the terms of the sequence all get close to each other. If the terms of the sequence all get close to A, then they get close to each other also, by like transitivity of closeness, also known as the triangle inequality of maybe division by 2. So let's try to use that. I'll try to draw a little bit of a proof. So let's let A and B a convergent sequence. So it has a limit. Let's let the limit be A. We then need to show, for the sake of Cauchiness, that no matter what epsilon you pick, there's a big N, so that if M is bigger than big N and N is bigger than big N, then what conclusion do we need?
Absolute value of A minus A is less than epsilon.
Nice. And I don't know if you said M or N plus because they sound the same, but it doesn't matter. I'm going to pause for a moment and try to like draw a picture of the proof. So there's AM, there's AN. I would like that distance to be less than epsilon. What's the thing that I know right now that I can get AM and AN both to be close to?
A.
So I can get both of those edges of this triangle to be as small as I want. If I want the dotted one to be length less than epsilon, then how small should I have the other two?
Less than epsilon.
Epsilon over 2, I think. Because then this one could be 2 epsilon. Cool. So, this tells us a lot. I can pick little m to be big enough so that this is less than epsilon over 2. I can pick little n to be big enough so that this is less than epsilon over 2. I want to pick little m and n both to be big, so that's good. So that this length is less than epsilon. Triangle inequality will do it. So let's put the words on the page. Consider any epsilon bigger than 0. Since an goes to a, there is some big n, so that if little n is bigger than big N, then absolute value an minus a is less than, well, I can put any positive number I want there. Based on the triangle that we just drew, what do you think I want to put there? Epsilon over 2. If you're not feeling brave, then instead put a box around this line and figure out what goes in the box by the end of the proof. So let's now consider any little m bigger than big N and any little n bigger than big N, which right is what we want to do. We considered any epsilon bigger than 0. Here's where we came up with our big N. It's not an explicit big N, but it can't be because I don't know the sequence explicitly. Let's suppose little m is bigger than big N, little n is bigger than big N. Our choice of big N lets us conclude that both of those are less than epsilon over 2. We need to show absolute value an minus am, and absolute value is less than epsilon over 2. And that like triangle picture also tells me what I want to do. I know that A is really close to both of them. So that tells me the thing I want to add and subtract. What do I want to put the next two blanks?
A.
Cool. And I don't know, do I have to actually write anything more for you to fill in the rest of this proof? Then I'll let you tell me what goes in this blank.
Less than or equal to an minus a and a minus an.
I'll put the absolute value back in.
Which is then less than epsilon, or less than epsilon over 2 plus epsilon over 2.
Yeah. Groovy. Does that feel pretty okay? So convergent implies Cauchy isn't the hard direction, it's the easy one. But it was actually, I think, pretty easy to pull off. The other direction, every Cauchy sequence converges. So this is going to feel dicier. So in order to show that its sequence converges, I need to come up with a candidate to be the limit. And I don't have a guess for the candidate to start with, so I'll have to figure something out. Maybe I'll start with this. Right, every convergent sequence is bounded, so if Cauchy implies convergent, then it better imply bounded. So every Cauchy sequence is bounded. Let's try to prove that. If an is Cauchy, then an is bounded. Do you remember when we proved in class that convergence implies bounded? But the trick we used is that boundedness is a really floppy condition. It just needs bounds to exist. Convergence or Cauchiness is a really strong condition. You get something for absolutely every epsilon. And you can take that epsilon and be really small and get really precise information. So let's just try to be floppy. Let's pick an epsilon that's just fixed and see what it tells us. I'm going to take epsilon equal to 1. So let's take epsilon equal to 1. Assume that an is Cauchy. So I know that an satisfies this condition for every epsilon. Let's take epsilon equal to 1, because I know it satisfies this, so it satisfies this for epsilon equals 1. It follows that there exists a big N, so that all this happens with a 1 at the end. So plug epsilon equals 1 into the definition of Cauchy. So there is some big N, so that for all little m and little n bigger than big N, absolute value an minus am is less than 1. So let's see, if we just fix some little m that's bigger than big N, is that an inequality you could solve for an? And you'd wind up with an being less than something and bigger than something else? That looks like a bound. Let's just do that. What's a reasonably explicit choice of little m that's bigger than big N?
N plus 1.
I know it's on the page. There's nothing fancy about y plus 1. You could do times 2, except then you might worry that, what if big N is negative? All right, so let's pick little m to be big N plus 1 and solve that for an. Solve that for an. What do you get? Let's do the scratch walk then. Oh, this note wasn't supposed to be there. Next time I teach, that's a note for me. Next time I teach this class, I think this letter should be homework. It's not right now. I forget that I actually use the notes to talk about them. I can't just write notes and whatever. Anyway, let's carry on. So I want to solve that inequality for an, where m is big N plus 1. So what do you do to that if you want to get a sub little n on its own? How can you get rid of those absolute values first? Cool. Nice. So now I guess just add the thing to the other side, to all the sides. So an plus 1 minus 1 is less than an is less than an plus 1 plus 1. That looks an awful lot like I have a lower bound and an upper bound, but it doesn't quite do the job. Because this bound only works once little n is bigger than big N. Big N could be 10 million. So I have a bound that holds once little n is big enough. But how many things are less than a billion? How many natural numbers are less than a billion?
How much billion?
Yeah, I think it's a billion minus one, but I might have it off by 1 error. The point is finitely many. Well, I can take the max and min of finitely many things, so let's just do that. As my lower bound, I will take the min between A1, A2, A3, all the way on up to A sub big N. And then I guess the thing that I know walks once little n is big. I feel pretty good. And in fact, what upper bound should I use then?
A plus 1 plus 1.
That definitely is something that's bigger than all a n's once little n is bigger than big N.
Do we want it to be the max of A1 through F?
Yeah. And that's a finite list. It might have a billion plus 1 entries in it, but you can take the max of a billion plus 1 nonetheless. And there, we got some bounds. Groovy. That feel pretty all right? So in the proof that convolution implies Cauchy, I'm going to need one topological fact. This is all I'm going to use the topology section for today. So the Bolzano-Weierstrass theorem for sets says that any infinite bounded subset of the real line has a limit point. And in fact, depending on how proactive you are with doing homeworks, you've already proven this. And I'll point out that the thing you proved is like the contrapositive of this. Flip back to the homework where you proved 5.2.13. Or maybe you haven't yet. It's like not due today. It's like the homework at the end of the compactness section. Yeah, I think. But like you have the statement. I suppose I do too. And it's homework, right? So it appears at the end. If X is a bounded set which has no limit points, then X is finite. So 5.2.13 says that. Any bounded set with no limit points is finite. So, that's like an if-then kind of statement, isn't it? It says if a set is bounded and has no limit points, then it is finite. So the set we have, the set we want to consider in the theorem, is it bounded? So it satisfies the boundedness condition. We want to prove it has no limit points. So I don't know, maybe you would think by contradiction. Let's suppose it had no limit points. Then this claim would mean that that set is finite. Is it finite? Nope. And this is essentially contraposition. Any bounded set which is not finite, negate the this, must have a limit point by negating the line that it has no limit points. That feel pretty good? And the proof of that, once you get around to it in the homework, is not actually that terribly bad, especially if you allow yourself to use the Heine-Borel theorem. All right. So now I'm ready to do Cauchy implies convergent, the hard direction. So I will let AN be a Cauchy sequence. I am also going to assume that sequences don't have elements, they have toms. The set of all toms of AN, I'm going to call that capital A. So it's the set of everything that looks like AN where n is a natural number. I'm going to assume that big A is an infinite set, which generally it is, right? If most of the sequences that you've looked at in your life don't only take finitely many values. Like -1 to the n is like weird like that. Extra credit, deal with the case that the sequence only takes on finitely many values. Let's start with this. Explain to me why that set big A is bounded.
It's Cauchy, so it has a limit.
Well, I want to show that it has a limit, so we better not assume.
It's Cauchy, so it converges.
That's what we need to prove. But what have we proven so far about Cauchy sequences?
They're bounded.
They're bounded. So I just want big A to be bounded. Can I give myself lines to do this? Oh, but we can do it anyway. So let's see. Since AN is Cauchy, lemma 6.1.4 says AN is bounded. Let's take L and U to be bounds. So those are bounds on a sequence. Are those also bounds on the set big A? Yeah. Elements of the set big A are toms in the sequence. These also bound big A. All right, so this setup is supposed to be really suggesting what the next thing we're going to do is. So I just arranged basically by assumption that the set big A is infinite in size. Now we know that it's bounded. What do we know about infinite bounded sets?
It has a limit point.
It's got a limit point. Big A has a limit point. By the Bolzano-Weierstrass theorem. So, by Bolzano-Weierstrass, A has a limit point. And let's think about why that's like a useful thing, why that's intuitively going to be useful. I need the toms of the sequence AN to get really, really close to a number. If the toms of the sequence are getting really, really close to a number, then the elements of this set are getting really, really close to that number. Well, that's a limit point. So, if this thing has a limit, it has to be that number A. Now I've got a candidate. Now I just need to use the assumptions and things that I've arranged so far to prove that A is the limit of AN. So here's the rest of the proof. We will show that A is the limit of the sequence AN. And we'll kind of draw a picture as we go. So right now I know that little a is a limit point for the set big A. We have like a handful of definitions for what a limit point is. Like there were 3 of them. Go look back in the notes. Grab me the one that says that there are infinitely many things. Yeah, we're doing it. We can do it this way.
Roll delta greater than 0. There are infinitely many little x and big X when the absolute value of little x minus u is less than delta.
Nice. So here delta is supposed to be the limit point. I guess big X, I'm going to have that be the set big A instead. And this delta I can pick freely. So here's why in the definition of things like limit points I didn't use epsilons. It's because I want to like translate a choice of epsilon to a choice of delta. So because of something that's going to be useful later on, and maybe we'll even draw a picture to see this, I'm going to take that delta to be epsilon over 2. So let's let A be a limit point of AN. This definition says that, well, epsilon over 2 is positive. So it says that there are infinitely many AN in the set big A such that absolute value of AN instead of X minus A is less than epsilon over 2. That feel pretty good? And that already looks like kind of close to the definition of the limit, right? Like it's not quite the definition of the limit. Instead this says that there are just infinitely many n's where AN is that close to A. It's not quite right, but it's getting there. And here's the payoff. I will now set A epsilon to be the set of all natural numbers M, so that absolute value AM minus A is less than epsilon over 2. So the line above just says that that set's infinite, right? So this set is infinite, and so in particular, it doesn't have an upper bound. Right, it's a subset of the natural numbers. So, now let's use Cauchiness. Since AN is Cauchy, there is some big N, so that for all M and N in N, if M is bigger than big N and N is bigger than big N, then so let's see what this means. I'm going to draw a picture that summarizes those two lines. So here's this limit point A. There's AM. So I can get that length to be less than epsilon over 2 infinitely often. AM minus AN, I can get this length to be less than epsilon over 2 as long as little n is bigger than big N. Could I arrange that little m is both satisfies this condition and that condition? Yeah, because there are infinitely many m that do that, so one of them has to be bigger than big N. So if we consider any little n bigger than big N, and any little m in N with little m in A epsilon, which exists since A epsilon is not bounded above, then let's do the same triangle inequality stuff. So if I've already written that, like, you know what's about to happen, right? Tell me what's about to happen. That's less than or equal to?
Absolute value of AN minus AM and AM minus A. That has to be less than epsilon over 2 plus epsilon over 2.
So we're done. Cool. So the hard bit was like trying to be sneaky and coming up with a candidate limit. Once we had it, as long as we like picked this candidate limit in a sensible way, the proof just fell out at us. And there are a handful of different proofs of the Cauchy criterion for convergence. This is the one that like is the most topological and actually uses topology. There are other ones that pass through a thing called the monotone subsequence theorem. There's another one that like considers a new sequence of the upper bounds on the sequence AN. But you know, this one's nice. It actually uses this notion of limit points. So, with the remaining few minutes, Let me say what's going to happen in the next couple days. So for homework, you just have this claim to prove. It'll feel very similar to the proof that we did at the beginning of class today. As an extra credit, you can prove that if a Cauchy sequence takes on only finitely many values, then it converges. And in fact, you can imitate the proof that we did before to just pull it off. Take a single value that the sequence takes infinitely many times. There's your limit. Use the argument we did in class to prove it. What's going to happen next time we meet is we are going to prove something which is like a really useful application of the Cauchy criterion. So the Cauchy criterion gives you a way of proving that a sequence converges without needing to know the limit in advance. And it's a little bit hard to get a hold of like what it actually means to prove a sequence is Cauchy directly. But there's a flavor of sequence that you can show is Cauchy, which is a so-called contracted sequence. And there's a definition there. We'll study that next time. But you can now fairly explicitly describe sequences that are contractive. There's a sequence that's kind of hard to make sense of what the limit should be. And so a Korn's relation, that's a little bit hard to solve. You can solve it. It's contractive, though. So if you can show that contractive sequences converge, that thing converges. You can also use this, and this will be done homework-wise. This will be like the group work for the day. To prove that there is a sequence which converges to the square root of 2. So the square root of 2 is, in fact, a real number, which is something that we haven't justified yet. Cool. So, I think I'm done for now. Anyone planning on coming to my office?
Indeed.
Oh, good. Yeah, you wanted to schedule a time to